Welcome to homework.
We're asked to determine the number of divisions used by the Euclidean algorithm to find the greatest common divisor of the Fibonacci numbers when they are consecutive, and to verify the answer with mathematical induction. So, recall the definition of the Fibonacci numbers. We have that f of 0 equals 0, f of 1 is equal to 1, and we have that f of n plus 2 is going to be equal to f of n plus 1 plus f of n for any n greater than or equal to 0. We want to prove that the number of divisions by the Euclidean algorithm for f of n and f of n plus 1 is n minus 1. When n is greater than or equal to 2. So, to do this, let Pn be this statement. Now, the basis step, I guess before we actually do the proof by induction, first let's consider the other cases. So we have that the number of divisions for f of 0, well, n is equal to 0, then we have that f of 0 is already 0, and so Euclidean algorithm requires no divisions. And the greatest common divisor of f of 0 and f of 1 is going to be equal to 0. Now, if n is equal to 1, then we have f of 1 equals 1, f of 2 is 1, and so we have the Euclidean algorithm requires exactly one division in this case, since f1 is divisible by f2. And now we'll move on to the base case. So now if n is equal to 2, we're going to execute the Euclidean algorithm. So first of all, we have f of 1 is equal to 1, and f of 2 is equal to 1. And then therefore we have that f of 2 is 1, and f of 3 is 2. And so we have that f of 3, which is 2, is equal to 1 times 1 plus 1, which is going to be f of 2 times 1 plus 1. So it requires 1, which is equal to 2 minus 1 divisions. I'm sorry, I made a mistake here. This should be f of 2 is going to be 2 times 1 plus 0, which is f2 times 2 plus 0. Since we have a remainder of 0, this means 1 or 2 minus 1 divisions. So now, for the inductive step, suppose that pk is true, we want to prove that pk plus 1 is also true. So execute the Euclidean algorithm again. So we have f of k plus 2 is equal to 1 times f of k plus 1 plus f of k, by definition, the Euclidean of the Fibonacci numbers. So this is one division here. And we have the next step. We're going to divide fk plus 1 by fk, which is the same as the first step of Euclidean algorithm. For fk plus 1 and fk. So the Euclidean algorithm of fk plus 2 and fk plus 1 requires one more division. So the total number of divisions is going to be 1 plus the number of divisions for fk plus 1 and fk, which we determined by the inductive hypothesis is going to be k minus 1. So this is k. And so we've shown that pk plus 1 is also true. And so, by the principle of mathematical induction, follows that Pn is true for all n greater than or equal to